Hey, welcome to The Explainer. Today, we're going to dig into three ideas that pretty much run our entire world: work, energy, and power. Seriously, they're behind everything, from lifting a book off your desk to launching a rocket into space. So let's jump right in.
So, what does climbing a flight of stairs have to do with powering an entire city? I know, it sounds a little out there, but the connection is absolutely real and, well, it's pretty amazing. The very same rules of physics that explain you huffing it up a few steps are the exact same ones that explain how we power our entire civilization. And yup, it turns out it has everything to do with it. The key is understanding these three totally interconnected ideas. Stick with me, and by the end of this, you'll see how work, energy, and power are basically the Lego blocks that build every single action in the universe. All right, first up, let's talk about work. And I don't mean your 9 to 5. In the world of physics, work has a super specific meaning. It has nothing to do with spreadsheets or meetings. It's all about applying a force to actually move something. So here's the official definition. Work is done when a force is applied to an object and causes that object to be displaced. The key words there are causes to be displaced. So think about it. If you push against a solid brick wall with all your might, but that wall doesn't budge, you've done exactly zero work in the eyes of physics. Doesn't matter how tired you get. If there's no movement, there's no work. Simple as that. So how do we actually calculate it? Well, the formula is pretty straightforward. Work equals force times distance. But what's a force? Just think of it as any push or a pull. We measure it by taking an object's mass and multiplying it by its acceleration. So when you lift something, you're applying a force against gravity's pull, right? And you're doing it over a certain distance. The unit we use to measure all this is called the joule. Okay, let's make this real. Let's go back to our stair climber. Let's say we have a 40-kilogram boy running up a 4-meter flight of stairs. We can figure out exactly how much work he's doing against gravity. We just multiply his mass, that's 40 kilograms, by the acceleration of gravity, which is roughly 10 meters per second squared, and then by the height, 4 meters. You crunch the numbers, and what do you get? He's done 1,600 joules of work. See? Not so bad. Okay, so if work is the action, what makes the action happen in the first place? That's where energy comes in. This is a big one. You can think of energy as the currency of the universe. You literally have to spend it to get any work done. No energy, no action, period. And this energy currency, it comes in all sorts of different forms. You've got mechanical energy in a moving car, chemical energy stored in a battery, thermal energy, heat from the sun. It's all the same fundamental stuff. It just kind of wears a different outfit depending on the situation. Now, if we zoom in on mechanical energy, it really splits into two main types. First, you've got potential energy. Think of this as stored energy. Our climber, standing at the very top of the stairs, he's loaded with potential energy. He has the potential to do work. The other type is kinetic energy, and that's the energy of motion. That's the energy he was actually using while he was running up the stairs. So we've got the work that's done, and we've got the energy to do it. But there's one more piece to this puzzle, and that's power. Power is all about how fast you do the work. It's the missing link that tells us how quickly all that energy is being used up.
And the definition is just beautifully simple. Power is the rate at which work is done. That's it. It's a measure of how much energy is being transferred or converted over a specific amount of time.
The formula is just as easy. You just take the total work done, remember our 1,600 joules from the stair example, and you divide it by the time it took to do it. The answer you get is measured in watts. Yeah, the same watts you see on your light bulbs every single day. And this right here perfectly explains the difference. Think about it. Whether our boy walks or sprints up those stairs, the amount of work he does against gravity is exactly the same, still 1,600 joules. But running takes way less time, right? So he's using much more power. He's spending his energy currency at a much, much faster rate. All right, now let's zoom out for a second, because these three concepts, work, energy, and power, they don't just exist in a vacuum. They're all governed by one of the most fundamental, most unbreakable laws in the entire universe. And that is the law of conservation of energy. It states that energy can neither be created nor destroyed. It can only be transformed from one form to another. This is a non-negotiable rule of the cosmos. The total amount of energy in the universe is fixed. It just changes its form, moving from one state to another, kind of like an actor quickly changing costumes backstage.
And you see these transformations literally everywhere you look. An electric motor, that's just turning electrical energy into the mechanical energy of motion. A generator does the exact opposite. A simple iron you use on your clothes, it takes that same electrical energy and transforms it into useful heat. The energy never disappears, it just gets a new job.
So why is this so important? Why does all of this physics stuff matter? Well, because understanding these energy transformations is absolutely central to how we power our entire planet. It brings us right back to that first question we asked about climbing stairs and powering a city. See, to do all the work that modern society demands, we have to tap into different energy sources. We usually group them into two big buckets: renewable, things like solar and wind that are constantly being replaced, and non-renewable, like our limited supplies of oil and natural gas. But from a pure physics standpoint, both are just different vaults of stored energy that we've figured out how to unlock and transform. The physics itself doesn't change. Whether we're burning fossil fuels or spinning a wind turbine, all we're doing is transforming energy from one form into another to get work done. The really critical part here is that the choice of which form of energy we start with, well, that's completely up to us. And those choices have enormous consequences for everyone. And that really leaves us with a final big thought. The laws of physics, like the law of conservation of energy, they're fixed. We can't change them. But our energy choices, those are not. They are flexible. So the real question for all of us is, what kind of world will we choose to power tomorrow?